Hello, there she is. Hello. Hello, Osmael. Hello. Well, don't
Good
look so.
afternoon, Professor.
Good afternoon. Thank you for saying so. Good afternoon and good afternoon. And where's the, didn't you have a chemistry thing on your wall last time? Wait, wasn't there a chemistry thing?
I do, but that's in my room. I'm in the living room right now.
Oh, right. Okay. Not to be, okay. Hello. Okay, wait, more people are coming in. Okay. Hello, Brian. Hello, Steve. Good afternoon, Montserrat. Hello. Oh, there's Abdel, top of the afternoon. Or did I be? And good afternoon, Stephen. Well, this is totally chaos. And you know why? Because the board has decided once again to wait. Okay. Top of the afternoon indeed. Okay, wait. I can't decide whether. Oh, and there's Jose. All right. And there is Ashley, and there's Tobias. Oh, yeah, to talk. I'm so glad I finally met Tobias, even though it was for like 1 second, and I was so rude because I was like juggling 14 Zoom meetings that all fell apart right before he walked in, but it wasn't his fault, even though I probably made him feel like it was his fault. It was totally not Tobias's fault. But at least now I know what he looks like, and he totally does not look like any Pokemon trainer that has ever been digitized in Scarlet and Violet or anything like that. What am I talking about? Okay, wait. So, and good afternoon, Montserrat, and hello, Jada. Oh, I saw Jada in 6 dimensions as well, and 85. There she is. Oh, in 7 dimensions. That's or 10 dimensions. That's awesome. She's the real thing. Okay. And there's good afternoon, Stephen. I'm going completely out of order. Hello, Brian. I already said that. Hello, Tobias. Right. Okay. Top of the afternoon, Abdel. See, I'm going through the chat now. That's why I'm repeating myself. Hell, Prof. Gianna's like sending me to hell. She's sending me to oops. Okay. It was just autocorrect. Yes, my phone always changes hello to hell also. Just kidding. Okay, good afternoon, Jose. So, but thank you, Gianna. No, I know you're not sending me that. Oh, yes, happy Thanksgiving Eve. Yes. Okay, we're gonna talk about that in a second. Good afternoon, Brianna. Wait, was that Brianna? Oh, Gianna, Brianna. Right. Sorry. Good afternoon, Miriam. Oh, you did. Wait. Via messaging. Okay, wait. I see. I vaguely understand. No, Gianna says. Okay, I take it all back, Gianna. I take everything back except for the nice parts. Good afternoon, Jasmine. Wait, and there's a direct via messaging. Messaging. Does that mean? Wait. Okay. Oh. Okay, but where did you send it? But where? Like in texting? Wait, I'm hearing you and I'm trying to be. Oh, I see. Okay, hang on. Okay. Uh, okay. Okay. Fair enough. I see. Okay. Wait, more people coming. I hear you. I hear you. Okay. Let me. I'm taking that seriously. Give me a second. And I'm talking to the direct chat person. He or she knows who he or she is. Totally reasonable request. I just give me a second. Okay. 2 things. One, all right. I'm getting to know more about, hello, Alejandro. Good to see you. And I'm very excited. Listen, I'm getting to know more and more of you in real life, and it really does mean a lot. I really do appreciate. I think it's better for both of us that I feel like I'm starting to know some of you as human beings on the 4th floor. I think it's terrific. And I apologize to those of you who've made an effort to say hello. And then if I was like rushing somewhere or something, I promise that's me being a spaz. You're still doing the right thing, and it does mean a lot. Seriously. And I think it helps me teach and helps you learn. Like really, like it's sort of easier for me to teach you if I think you're a real person. And it's easier for me to meet you halfway on things that you need. So on that, it is true. Some of you already know I still don't have the exams. First of all, I still don't. I apologize. I do care about them and about you. I failed to get them for Monday, and I kind of knew, and some of you who do know my schedule, once I didn't get them for Monday, I knew it was going to be pretty impossible to finish them for today, and indeed I didn't. I will still keep working on them over the holiday, I promise. you will not have new homework assignments until of any real, until I get them back. You only have like 1 or 2 more real homework assignments until the final anyway, but you won't have until I get these back. If you have any catching up to do over the break, please do that. But other than that, have a break. In terms of the break, and I'm also trying to get my board back up again. This is always the board. But someone just did ask me, why are they making me? Like, I literally just used this board this morning. Why now did I have to resign it? Excuse me for a second. But also, there's this funny thing at John. I know it's the day before Thanksgiving, and I'm excited for you, and I'm excited for me that it's Thanksgiving. And I know this is a classic thing. John Jay always goes right up to the last minute before Thanksgiving, and it's terribly annoying. I know. It always goes through today all the way to tonight. I used to teach that Wednesday night lab, and it drove me crazy. I mean, I happen not to teach it now, but I know you guys have it. So I just got a very reasonable request about that lab. I totally hear you. Oh, wait. North Carolina. All right. Oh, sorry. I lived in North Carolina for a year, just saying. A long time ago. Here's remind me, because I don't want to get myself in trouble with, I mean, who do you have tonight? Do you guys have you're all in the same lab, I think, and it's tonight. Is it Professor Walters that you have tonight, or Professor Lou? It's Professor Lou? Wait, which? It's Lou. Okay. Oh, right. Of course. What lab are you doing tonight? Do you know? 5. Part 2. Slow down, week 2. Okay. We're on week 2 of that. By the way, thank you for all the answers. I see. Thank you. Oh, seriously. Wow. Oh, wow. All of you. My God, you're paying such attention. Thank you, Kay. Thank you, Abdel. Thank you, Gianna. Thank you, Kay. Thank you, Jada. Thank you, Abdel. Thank you, Gianna. Thank you, Ashley. Wow. Abdel. Okay. So listen, a couple things about that. First of all, as you see, you're a little bit, what we're doing in class right now is all meant to help with that lab. Like that lab, and this is not to get out of the question, but just to be clear, that lab, the problem that you're studying that lab is like the super hard, super complicated version of everything I'm trying to show you right now. In other words, like today, we're going to start doing free body diagrams. I know that already it's assumed in the lab that you sort of are doing them, but you're kind of doing them in the dark. You're kind of, making it up as you go along. And it's hard. I'm trying to give you the basics here in lecture of how to do the free body diagrams and stuff. Right now, to some of you, it might seem like boring or like a day late, dollar short, like, because you're already trying to make a very complicated diagram in that lab. I am here to tell you that once you have all the basics from what I say in class, then they literally do apply. You just have to carefully apply them to know what to do in the lab. Everything I'm trying to do right now, in other words, is to help you complete that lab, and particularly to do the lab report. So for whatever it's worth, the lab is still a little bit ahead of where I'm in class. But if you keep taking notes and stuff like that, hopefully what we're doing in class today and what we'll finish on Monday will very much help you write that report, since it's not due yet. And in fact, I'm going to make a point of, by the end of Monday, I will literally explain things of literally what to do with that lab for your report and stuff, because it is hard. But it's all based on what we're doing in class right now. Now, that all said, yeah, I'll be as honest as I can as part of a Thanksgiving gift. In my heart of hearts, do I think it's reasonable for some people to be advocating for the whole groups and very politely suggesting to me that maybe they could go a little early for once because it's Thanksgiving? Do I think that's reasonable? Absolutely. Do I also want to get to Thanksgiving? Absolutely. I can't literally say yes because I'm not your lab instructor. Like, am I, and I don't, and this is, I don't want to do a mommy daddy thing. Like mommy says it's okay if daddy's or whatever, like, cause that gets awkward. Like, does the original rule that no one can ever leave early from lab originally come from me? Oh, yes. I mean, and am I the one that ultimately enforces that, enforces all the lab? Yes, it's all on me, that badness. Am I willing to send a small text to Professor Lou and say it's okay with me, if it's okay with her, if people finish early, that they go early for Thanksgiving? Yes, I'm willing to do that. I'll do that in 2 seconds. But I do want to warn you that it's a little bit awkward because I don't like I'll do that. I'll suggest it to her that it's okay because of Thanksgiving and all of that. But then I'm going to let it go and I'm going to ask you guys, I'm talking to all of you. I think it's a reasonable request, but because we all run our own different turfs and all that stuff, and because I have nothing but the deepest, profound respect for Professor Lou, and that's a whole other story I'll get into. I mean, but I mean it. I'll send her a text just saying, if she wants to think about it, that's cool. But then I'm going to let it go. I'm not going to wait for a response. I'm going to ask you guys, just go to lab. If she wants to take my text, if she gets the text in time and she says to you, you can go early if you finish early, then great, then we all win. But I would say that if she doesn't say that, don't ask, don't push it, because that means she's then made an independent decision. And I don't want to, and it's not, I don't want to play good cop, bad cop, like with you guys, with her, if you know what I mean. It's like really easy for me to be the nice guy sitting here when I don't know exactly what she needs you to get done or this or that. It's easy for me to say the nice thing and then let her look like the bad person. And that's like that's an obnoxious thing for me to do. So okay, so like I'm going to say in a moment, I'll just send a quiet text just saying, you know what, if it seems reasonable in honor of Thanksgiving, feel free. And if she does, she does. But if not, let it go. And I'm going to tell you, now that we're talking about this also as part of a little Thanksgiving thing, just so you know, so Professor Lou's been teaching with me for a long time. And she's been holding together this physics program, a lot of it for a long time. Like we had a physics faculty that I loved dearly that lasted forever until COVID. And then COVID came and we started dropping like flies one after another. And she's been one of the stalwart people that has stayed here through COVID, through having a family of her own, through all these other things. And she's been running 101, like physics 101, which I know you don't take, but just so you know, she's been single-handedly running all the sections of 101 while I look at other things like 204 and 203. She's like an amazing anchor of this whole physics program and has been here a while. And as you may know, she's actually also leaving. I don't know if you know that or not, but she's moving on to bigger, more lucrative things, and God bless her for it. Like, that's great. But you know that even though she's leaving, and we already had got new, maybe I'm saying too much, but just so you know, we already put new people in place for all of her other classes for 101 and all that. But even though she has a new job and all that, she literally is staying on and comes to John Jay just to do. I mean, I should not be saying this, but she stays connected just to keep doing. And she worked out a schedule to keep doing now you're going to feel guilty, but to do your lab, because she wanted to keep doing your lab and stay connected with that and see it out to the end of the semester and not have you guys have a new teacher like come in the middle, because that's so annoying. So she takes this lab very seriously. And she comes in for it. So if she has an idea of like, no, I'm coming all the way in and I'm giving up my Thanksgiving night, or pre, so they can too, then I want you to know that maybe is what's going on. I'm going to send a text because I see it both ways, but she's an awesome person in my judgment, whose judgment I totally respect. So I don't want to mess with her. And then last thing I'm going to say, I'm so afraid of what's in. Oh, okay. Thank you. Okay. Sorry. I'm totally, wait. Oh, okay. Oh, sorry. I'm looking at the chat. I'm so out of it. And I appreciate the person who asked me about it. I totally get it. It's a totally fair question. And I don't mean to be making a big drama deal, but I think really there's a real sadness in my heart that she's leaving, because I mean, she's actually been here the longest out of everybody besides me. I mean, but I'm going to send her a text, and I know you guys work very hard for her and all that. But also, just side note too, when I say she's leaving, just so you also know as motivation, I'm sure I've mentioned this before, when I say she runs 101 and she runs all this, and now she's going on to more lucrative things, and she's been a professor for us for a long time, and along the way she got a master's in physics from Hunter, like, you know, built up her resume and now can really all this, you know, just so you know, where did I meet her first? Guess, if it's not already obvious, where did I first meet Professor Liu? And where did I first start to take such an interest in her talent and her ambitions and her strength as a person? In Physics 203. She was a student in Physics 203 and then in Physics 204. I mean, and now she has like a whole career like opening up in front of her from all of this. So, you know, again, I guess I've told you this. Oh yeah, I told you other stories before, but real life can emerge from success at John Jay or from doing the right thing at the right time at John Jay. And we're always looking for replacements. So keep doing well in 203. Okay, so hold on. Oh yeah, totally. Yeah, no, she was my student. Yeah, I mean, and I could say that now because she's leaving, but everybody who teaches physics here was my student at one time or another. I mean, that's how it works. Like you do well, you know, you rock the classes, then you become a lab tech, a CLT, or a tutor in the MSRC or something like that, and you work your way up, and then you get a job and another job, and then you're called professor, and then you go out and make a lot more money and raise a family. That's how it, yeah. I mean, she was, everybody you ever have in physics was a student of mine at one point or another. This shit can lead to real shit. Excuse my language. No, I'm not a legend. No, that's very nice of you to say, but no, what I am saying though is, well, you know what I'm saying. I'm saying there can be fruits at the end of the line to all this. Also, you know what, I'm going to say one other thing that's important about all this is if you didn't know that, here's possibly the most inspiring thing I could say about that whole story to any of you. And she wouldn't mind me saying this at this point. Yes, she was a student of mine. And yes, she rocked the course. I mean, I thought she was awesome. And I thought she was super smart and super cool and all that. And then same thing in Physics 204 and all that. But let me tell you this. When she had me for 203, it happened to have been the first year I was at John Jay. I mean, so it's going back a ways, but when she had me for 203, and yes, she rocked the course, let me tell you all something super important. That was the second time she was taking 203. The first time she took 203, she failed it. Now that happened to have been with a different professor, the professor that I replaced. Okay, but that's not, but that does, I mean, I don't know what that means, but I'm just telling you, she failed physics the first time, failed it, took it again, and then happened to be with a new professor. But in that second, and she was a jerk in class. And she knows that I think this. I mean, she had attitude in that class. Like she had attitude, but she was clearly talented. What I'm trying to say is everybody's story is complicated and everybody gets to wherever they're going in a complicated way. She failed physics the first time, and she's possibly the most influential, like successful, important physics professor at John Jay. I mean, besides me, no, like seriously. And she's leaving only because bigger and better things are opening up for her. So I'm saying this to all of you that there is a lot of us have to do things more than once to nail them. But there's second chances for and I knew that believe me, I knew what her background was when I started offering her other jobs and stuff like that. A whole other story, but I'm just saying, all of you, there's second chances and third chances and forgiveness and compassion and understanding in all kinds of areas of life that we often don't think. You can fail and it's okay. Failure is not a failure. It just means I got to do this again, or often. I mean, sometimes it doesn't, but often, right? So don't any of you, even if you think you're not doing well in this class or something like that, maybe it just means I'll see you again and we'll get it right the next time. Honestly. Okay, but wait, but hopefully you see what okay, now I'm gonna get my board working, but oh no, I'm gonna pause, I'm gonna text her. I'm gonna get my board. Give me a second. Okay, all right, so I did that. Okay, so now I'm trying to get back on my board. Okay, the board's coming. So thank you for indulging that. I just text her, just so we'll see. But if she does, she does. If she doesn't, she doesn't. But never give up on yourselves. That's what I'm saying. And stick around so that you and I, whoever you are, and I can, in fact, what? Oh, stick around so that you and I can work together in physics classes in the future to come. And so you can oppress the next generation. Okay, here goes my board. Okay, all right. So what we're gonna do now, wait, who else do you? Yeah, don't get me another time. I'll tell you stories about the other I mean, God, there's definitely stories about the history of this physics faculty. But I'm very blessed. They're all awesome because they're handpicked. Okay. Well, so again, I apologize. I don't have your exam. Well, I said that already. All right. So we're going to go back to the material now. This material is all to build up to help you with that lab. Let's go. Let's go. Please stop me at any moment with questions. But now I'm just going to start going, if that's okay. All right. So what we did on Monday was we did system schemas for 3 different cases. And the whole idea of the system schemas was that you draw a system schema to figure out what forces are acting and how many there are. Because again, that's actually the tricky part of physics, is to figure out what are the forces acting on a given mass. You draw the system schema literally to find out what the forces are. And you do it by doing these tests in your mind. Like, okay, first of all, is there planet Earth? Yes, there's planet Earth. And second of all, is there anything touching this object? Anything touching the object gets a solid circle in the system schema. And then you say, okay, for each of the things touching my mass, I'm going to draw a line from each of these objects to my mass. Then you say to yourself, are any of these objects, do they happen to be a surface that's pushing on my mass, as opposed to like a line pulling on my mass? If they're like a line, like a fishing line or a string or a rod pulling on my mass, then I just leave it. I just draw one literal line to represent that pulling force. But if it's a surface that's pushing on my mass, then I follow this rule that says I'm going to draw 2 lines, right? Especially if it's a rough surface. I draw 2 lines, right? So I follow these rules. I draw solid circles for everything touching my mass plus a solid circle for Earth. I connect all those solid circles to my mass with straight lines. I look to see if there's any situation where I should draw 2 lines, which again would mean any surface that's pushing on the surface of my mass. In that case, I would draw 2 lines. Again, why? Because we think in the real world, when rough surfaces push on each other, they actually exert 2 forces. They exert a force like that against one another along the axis perpendicular to the plane of contact. If this is the plane of contact, when my 2 hands push against that, perpendicular to it, we call that the normal force. But normal just means perpendicular. But then we say anything, we say in the real world, when rough surfaces push on each other, they automatically get interlocked because they're rough. So microscopically, they're like at these ridges and nooks and crannies. So any 2 surfaces that push on each other get interlocked and then cause a resistance along the sliding rubbing axis, along the sliding rubbing direction, which is the axis parallel to the plane of contact. And we call that sliding, rubbing, resisting force, we call that friction, right? So we say when any 2 surfaces push against each other, they also automatically push against each other. So anytime in the system schema, we see a solid circle that represents some kind of surface pushing on our mass, we give it 2 lines instead of just 1. We say there's 2 forces acting. One we call normal and the other we call friction, right? So then that was what we did Monday. I'm just quickly reviewing what we did Monday. So then we have this system schema, which is all of these objects surrounding the mass of concern. And all of the objects are exerting forces on our mass of concern. And and we've done all that so that we can identify all the forces. We step back when we're done with the system schema and we look at it, and every single, if we've done it correctly, which we will have done it correctly if we just follow the rules. Like, in other words, we don't have to think, we don't have to invent the wheel. If we just follow the rules, which is what many of us are looking for in physics and never found in the first chapter of this course, or the first part, if we just follow the rules, we'll have a system schema now where every single line in the system schema is a force, that where the number of lines in the system schema is literally the number of forces that we're going to have to now account for and add up to do the math to solve for F net equals ma, right? So the purpose of the system schema was getting our thoughts from objects in the universe that are identifiable, noticeable, tangible, discrete, material. It's getting our mind to from that way of thinking to noticing the interactions that are happening. So the system schema, you draw the circles to make the lines represent forces. And now what we do, and I'm going to turn the page in a minute, what we do with those lines is that every one of those line segments, every one of those line segments in our system schema is now going to become a vector arrow in a pure free body diagram. So now we're going to draw a pure free body diagram from the system schema according to rules I'm now going to give you. So I'm going to show you exactly how you draw a free body diagram. Again, I know you've already been doing it in lab, but some of you have been sort of doing it in the dark, and some of you are more confused about what you're doing than others while you're doing it. Some of you are just whatever. So I'm backing up and explaining what's supposed to be happening with these free body diagrams. In principle, the best way to make a free body diagram is to start with a system schema, whether the lab asked you to or not. It's just the best way. Every line in the system schema is now going to become an arrow in the free body diagram, and I'm going to show you how to do that. And I'm going to do just like we did Monday, building in cases for the same 3 cases that we did Monday. So here we go. So, okay, so to draw a pure free body diagram, here's the first 2 rules. I'm going to read them out loud in a second. Okay. The rules are, first of all, draw a dot on your page, like somewhere in the middle of your page. The dot represents the center point of your mass at one point in time. Okay, so like in the system schema, we drew a dotted circle to represent our mass. Now in the free body diagram, I highly recommend the traditional thing is to draw a dot representing your mass. And it's trying to emphasize that what we're looking now, we're going to examine or consider your mass at one point in space, at one point in time. And that's what forces act on. Forces act on one point in space and one point in time. I know, by the way, that on the web, there's lots of different ways to draw a free body diagram and lots of fewer ways to draw a system schema. On the web, sometimes they won't do a dot, they'll do like a square or a circle. It's fine. I'm not going to get into like a whole argument about that. I wouldn't take off points on your final exam if you did another way, but can I suggest that I think the traditional classic way, for good reasons, is to draw a point representing your mass. Okay, so you do that first. Then what we're going to do is we're going to look at our system schema, and for each, what it says here, instruction number 2, for each and every line segment in our system schema, we're going to make an arrow emerging from our point. In other words, every line you see, you're going to turn it to an arrow. Every line you see in that old diagram is going to become an arrow in this new diagram. You're going to start the tail of the arrow at your dot and then go off to a tip. Okay, and obviously I'm going to do this for you in a second, but those are the first 2 rules. And then each arrow is supposed to be a vector. So it's meant to represent direction and magnitude in whatever order you want. They both matter, direction and magnitude. Each arrow will point in the direction toward which the force is pulling or pushing. So you'll see in a minute, for example, like if you think that, so yeah, if you think the Earth is pulling down on your mass, if you think the Earth is pulling your mass down toward Earth, you're going to draw an arrow pointing down, like duh. The tail of the arrow will be at your dot, and then the tip will be below your dot, okay? So the arrow points in the direction that the force is like actually acting, so far as you can tell. The length of each arrow should approximately, qualitatively, comparatively represent the magnitude of the force. Okay, this is a little bit subtle. I say approximately, qualitatively, comparatively. What I'm saying is any force in your situation, any interaction in your system schema that you think is really, really strong, if you have some reason to believe it's really, really strong, then make the arrow really, really big. If you think it's really a weak pull or a weak push, then you make the arrow really small. That's basically all I'm saying. Don't kill yourself to make the arrow's exact lengths, because the truth of the matter is, if you actually knew the exact magnitudes of these forces, we wouldn't need to be doing all of this. We're doing all of this in order ultimately to compute and discover the exact magnitudes and directions of these forces. So it's very possible you don't know exactly how strong or weak the forces are when you begin. And that's, I don't want you to get upset over that or confused. You don't probably know exactly how strong any particular force is. But if you have an idea, a rough idea that this force is probably a lot stronger than that one, or if you have a rough or good reason to believe that these two forces might be equal, okay, then make their lengths equal. But it's a predictive, approximate sense that you're trying to give yourself. It's not an exact thing. Okay, so you make arrows, the direction is relevant, the magnitude is relevant. And then finally, it says here on the side in 2C, like off like this, it says, label each arrow with symbols or names, but not with numbers. You'll see what I mean by that in a minute. But so you're going to make arrows, you're going to label each arrow. The labels are going to involve letters and words and things like that, but don't try to put numbers on the arrows, because again, the whole purpose of this is ultimately to compute the numbers. If you act like you know the numbers from the beginning, something is going to get confused and wrong. Like we don't know all the numbers from the beginning. Okay, so this is the general procedure. Obviously, I'm going to get more concrete in a second. All right, so here we go. Example 1, free fall, right? So I drew my dot in the center of the page and I labeled it M for mass. You can do that. And then I look back, I mean, I'm not doing it right here, but you look back at your system schema for free fall and you notice that system schema, we had a dotted circle for M, we had a solid circle for planet Earth over here, and we had one line connecting them. So one line, there's only going to be one arrow in our picture here. That one line represented the pull of Earth. Earth pulls us down toward it, so I make this arrow go down. That one pull from Earth we call gravity or gravitational pull. The most common, classic, ultimately most helpful word for that force is the word weight. That's a word we started using in the system schema. That's the word I use here. So I label this arrow right now for the moment with the word weight. Like I don't put any numbers in, but I just call it weight, meaning the pull of gravity, okay? Now that's my whole system schema in a way. It's not, if you're uncomfortable, if you're like, wait, he puts the word weight in there? I thought they were supposed to put something else from the lab. Yes, I'm getting to that. I'm just going to show you where that other thing comes from. But for the moment, I'm writing the word weight. So I'm going to pause. Okay. So I'm putting the word weight. Just notice the real main thing that's happening here is we're changing line segments into arrows. We're gaining the information of direction. When we move from a system schema to a free body diagram, what we're now becoming precise about direction. Notice that in the system schema, there was nothing implied about direction at all. Like the Earth, we put wherever we want in the picture, above our object, below our object, we don't care. There's nothing about up, down, left, or right in our system schema. We're getting that established now in the free body diagram. You might ask, then what's the purpose of the system schema? Like why? Because the system schema was where we first figured out what the forces were at all. And the only way we could figure out what the forces were is that we first thought about the objects that were exerting the forces. The whole idea of the system schema is to make sure that we never invent a force that's coming from nowhere. Because honestly, people do that all the time. What we're trying to avoid is just making up a force that we just think should be there for some reason. We always remember that a force is an interaction between two objects. So the system schema forces us always to have two objects interacting in order for us to believe that there's a force. And then we draw a line in between them, and that's the force. But then when we go from the system schema to the free body diagram, we pick up the information of direction and we drop the information of the other object. Like, notice now what is here is the down arrow, but what's not in this picture anymore is Earth itself. Earth is gone now. We used Earth to convince ourselves that there was a force called gravity. Now that we believe in the force called gravity or weight, now that's all we care about from here on in is that force that we've now in our minds disembodied from planet Earth. Like, we only believe in it because we believe in planet Earth. But now that we believe in the weight, that's all we're going to look at now. So all that's left in this picture is just this down arrow labeled weight, okay? Direction is gained, other object is lost. Now, what's the purpose of the free body diagram? Again, obviously this is a simple one, but everything that we do is based on this simple one. So I'm dwelling on it for a minute, for an hour. The purpose of these free body diagrams is that you use them to solve F net equals ma. You use them to solve for acceleration or force according to Newton's second law of motion. So let's stop for a minute and see how that works with this seemingly simple example. I'm going to write down, because this is what you do. Once you have a free body diagram, especially or a component free body diagram, you then take the information of it. You take all the forces in your diagram and you plug them in to the left side of F net equals ma in order to learn to solve for something. So I write down at the bottom of the page, F net equals ma. It's a vector equation. Sum of all the forces along each axis independently but simultaneously equals ma along each axis independently but simultaneously. So I go to the next page. Now, often, what it says here is often what we use net F equals ma to add up all the F's and then solve for A. That's usually what we do with all these pictures. In this case, in this simple case, we're starting with simple case because it happens here in free fall. We already know the A. If something is free falling, A is G, lowercase g. That is to say, if something is free falling toward Earth, its acceleration is approximately 9.81 meters per second squared. If it were falling toward the moon, it would be 1.16 meter per second squared or whatever. But whatever that number is, or if we're measuring in feet, it would be 32 feet per second squared. Whatever that number is, we call it lowercase g. We know the acceleration of an object in free fall is g. So I already know that. So I'm going to plug that in for A, and I'm going to see if I can use that acceleration information to learn anything about the forces. I'm going to go kind of in the backwards direction here in this case. So I go to the next page. So how do I do it? It says F equals ma is a vector equation. Oh, that down arrow is not meant to mean what it looks like it means. Okay, so F net equals ma is a vector equation. What that always means, I want to establish this, and this is really important for your lab, as you might recognize. I want to establish this habit. When I write down F net equals ma as a vector equation, what that really means is F net in the y equals ma in the y axis, while independently but simultaneously F net in the x equals ma in the x axis, and F net in the z equals ma z. Like, it literally, F net equals ma, the vector equation, really always means three independent but simultaneous equations along each of the three independent but simultaneous space axes. All right, now, but in this case, there's only one axis where anything is happening. There's only one force, and it's acting on one axis, the y-axis. So I'm not worried about, so I just wrote this all down. Whoa, did not mean to do that, sorry. I wrote this line down to enforce like a habit that you should get into, but it's not relevant here. We just have sum of all the y forces equals ma in the y-axis. So I plug in my habit that I'll always do, no matter how complicated the thing is, even your lab, I start plugging in all of like all of the words from the arrows in my picture along that axis, I just put him into the left side. So there's only one force in my picture. There's only one arrow. It's the arrow of weight. So I write weight on the left side. Weight equals ma, a meaning acceleration along the y-axis. But as it says here, we already know a. We know the acceleration along the y-axis is g. And that sounds redundant, but a just means acceleration in general. G means specifically like 9.8 or whatever. So I plug in G. And now what I find at the bottom of the page, and again, I know you kind of know this from lab, but let me just indulge me and let me just show you where it came from or be as clear as I can. What we just learned by doing this simple example of free fall, doing the simple free body diagram of free fall, is apparently weight, the force of gravitational pull from planet Earth, equals m times g. Weight, the force of gravity, does not equal g. G is acceleration due to gravity. And it doesn't equal m. M is mass. But it does equal m times g. From here on in, as I think you know from your lab pictures, from here on in, wherever we might have written down the word weight, we can just abbreviate that with the mathematical product m times g. Let me be, from now on, we learn this from free fall, but it's true in all cases, even when something's not free falling. And remember, in all cases, even when something's not free falling, in all cases, weight is there. Weight is always a force in every single system schema, in every single free body diagram. It's the first one we draw because it's always there. And until today, I would have labeled that arrow that I first always draw with the word weight. But now I'm saying from here on in, if I want to start doing some math with this, I can always write down mg, always. In other words, what I'm saying here, from the example of free fall, we just learned that in general, even when things aren't free falling, that weight of an object equals the mg of that object. Weight is a force, specifically the force of gravity, but it's a force, it's measured in newtons. Your weight in newtons equals your mass in kilograms times the free fall acceleration due to gravity measured in meters per second squared. In other words, a mass of 1 kilogram in the net metric system, a mass of 1 kilogram has a weight of approximately 9.81 newtons. Mass measures kilograms, newtons measures weight. What's the difference? And again, believe me, I know you've heard this a million times, but honestly, I heard it a million times too, and I understood it on the 1,000,003rd time I heard it. I mean, all respect, like the difference between mass and weight is a huge difference. Mathematically, it's a difference of just multiplying by 9.8, but conceptually, the difference between mass and weight is mass, and you may want to write this down, well, mass, m, by definition, is F net divided by A. What mass is, and I know in chemistry, something, well, what is mass? It's like how much stuff there is in an object. Well, yes, but what does that mean? Like, what does it mean for an object to have a lot of stuff in it? What does it mean for helium to have a higher atomic mass than hydrogen or whatever? Like, it doesn't mean volume. You know that. You know mass is not volume. And you know mass is not density. What is mass? Like, really, what mass is resistance to acceleration. Some people even call it inertia. What we mean when we say that my brother is twice as massive as me, like he's not literally, but my brother's an FDNY. He's bigger than I am. Let's say my brother has 2 times the mass that I do. What that means is if you want to get him up to a certain speed in a certain time, like if you want to push him so that he goes, so he was standing around, you want to push him so that he's going 2.5 miles an hour within a second of pushing, and you want to do the same thing to me, you want to get us each up to the same speed in the same amount of time. My brother, you would have to push twice as hard to get him up to the same speed in the same amount of time as me. Or put another way, if you pushed my brother and you pushed me, the same amount of strength, the same amount of force, I would go twice as fast in the same amount of time as he would. I would accelerate at twice the rate as my brother if you pushed us both with the same push, because I have half the mass. And by the way, that's even if you were pushing us horizontally. Like mass itself has nothing to do with gravity or pulling up or pulling down or anything. Mass, it's twice as hard to get my brother up to speed, I mean, physically, as it is me. And that would be exactly as true on the moon as it would be here, right? It has nothing to do with gravity. It's just he resists changes in his motion twice as much as I do if he is indeed twice as massive as I am. Mass is resistance to changes in motion. That's what mass is. Now weight, and it's measured in kilograms. And it goes in the right side of F net equals MA. It's inversely proportional to A, when subjected to the same F. That's what mass is. Weight is a force. Weight is how much I'm being pulled down by planet Earth. It's a totally vertical phenomenon, right? And even when I'm not falling down, even right now, I'm not falling down, but that's because a chair is pushing me up. And the chair, in order to keep me from falling, has to support my weight. Weight is the force pulling me down. The chair is exerting a force up, stopping me from falling, so I'm cool, okay? But those are forces. Weight is a force exerted on me by planet Earth. It happens to be, for some reason, it happens to be my mass times the number 9.8. But if I went to the moon, it would be my mass times the number 1.16. Like my mass would be the same on the moon, but my weight, my downward pull, would be a lot less. To push me up would be a lot easier on the moon than here. But pushing me over is the same, either, okay? So weight is a force measured in newtons. Mass is a resistance, an inertia measured in kilograms. So from now on, bottom line, from now on, in every single free body diagram we ever draw, including the ones in lab, the first thing we'll always draw is a downward arrow representing the pull from Earth, because it's always there and it's always in our system schemas. And we're going to label that downward arrow mg, and that not g and not m, mg. And that means the weight, the pull from planet Earth. Okay. That's what we got from that. I'm just looking at the time. We've got 25 minutes. Oh, we can solve the problems of the universe. Okay. So now that was the example one, free fall. Now we're going to go to a slightly more complicated example. And obviously we're trying to build towards your lab. Your lab is the most complicated. It is a very complicated example. But with these simple rules, you could do everything you need to do in your lab. All right. So next example. So from here on, so from now on, free fall, the picture would just be a downward arrow, and I would just label it MG, like I just said a second ago. And that arrow is now in every single diagram, even when things aren't free falling anymore. Like this, we used free fall to show that the weight of something, whether or not it's being supported, is MG. Okay, so that's that example. Now, case two, back to the case from Monday. So we have a fish of mass M hanging from a fishing line. So let's say the fish is stationary. I'm just saying, for example, it doesn't have to be, let's say. So I looked at my system schema. In my system schema, there were two lines in the system schema, right? One line that went off to planet Earth, and one line that went off to the rope, or the fishing string, the nylon, the fishing line, right? So I had two lines in the system schema, so they become two forces in my diagram. Now, one of them is always there. It's the mg force. I always draw it first. It's always there. It's pointing down. Then I draw an arrow to represent the rope. First of all, I believe that arrow is pointing up. Why do I believe that arrow is pointing up? Well, number one, it's pulling on the fish. It's not pushing on the fish. It's not a magnet. It's pulling on the fish, and it's above the fish. To pull means to bring toward. To push means to send away. So the rope is above the fish. So it's pulling the fish toward the rope. That's in the upward direction. That's one reason I believe that the arrow representing the rope must be pointing up. But the other reason I believe that is if the rope weren't there, the fish would fall down. But the fish isn't falling down. So that rope must be pulling up. In effect, I'm using Newton's second law in my mind. So there's a rope pulling up. So I have an arrow pointing up. And we said in the system schema that anytime you have a one-dimensional material, like a rope or a string or a rod, anytime you have a one-dimensional material that's exerting a pull on something, like so one-dimensional, like a line, and exerting a pull, like not a push. So I'm really saying anytime you have a rope or a rod or a string, as opposed to like a surface pushing another surface, but anytime you have a rope or a line pulling, we say that the force exerted, the pulling force exerted by that rope or that line is called tension. So I'm labeling it with capital T for tension. Okay, so here's my diagram. Tension up, gravity down. Tension is not in every single diagram. It wasn't in the free fall example. It won't be in the next example we do, but it's in any example that has a string in it. Similarly, the normal force is not in this diagram. There is no normal force in this diagram, even though the word normal makes it sound like that force should normally always be there. Please note, especially since you're thick in the lab right now, notice here's a diagram that has mg in it, but there's no normal in it. So please recognize the normal force does not automatically or normally come along just to counterbalance gravity. People always think that. A lot of web pages think that it does, but it doesn't. And even when it is, and another lab hint, even when there is gravity and there is a normal force, there's no assurance at all that the normal force will be opposite in direction to gravity or equal in magnitude to gravity. The normal force does not have to have anything to do with gravity, and it doesn't have to be there. Normal force just means two surfaces pushing against each other. The normal force will point in whatever direction one surface pushes against the other. So in terms of your lab, like if your track is like this on an angle, then your normal force is on an angle. I mean, I think most of you know that, but just notice the normal force is on an angle in the lab. mg is not. mg is always straight down, and mg is always there. It's the only force that's always necessarily in every single diagram. Some diagrams have tension, some don't. Some diagrams have normal, some don't. Some have friction, some don't. This one has mg down, tension up, two arrows that are opposite. Now, do I think they're equal? Did I draw them kind of equal in length? I drew them kind of equal in length. I kind of have this sense that they might be equal in magnitude. And I think I'm even right. But am I sure? Like, where am I getting this idea? Why do I think these two arrows are equal in magnitude? Well, let's see. Let me go to Newton's second law, because that's what, now I have a diagram, right? I'm pretty confident of it. The only thing I'm not sure if T and mg should necessarily be equal size. I think they're roughly, but now that I have a diagram, let me do what I'm always supposed to do with diagrams, which is set up F net equals ma. I'm going to write the sum of the forces equals mass times the acceleration. And I'll see what I can see about force magnitudes and acceleration magnitudes. So I write down F net equals ma as a vector equation. And it's a vector equation. So it's true in the x direction, it's true in the y direction, it's true in the z. So it's true in all, but the x direction there don't seem to be any forces on the x direction. There don't seem to be any forces in the z direction. So that's true, but I cross them out. I'm not going to do anything with those. So I look at the y-axis. Sum of all the y forces equals ma in the y direction. So I write that down, bottom of the right, I've written it down. So now I go to the next page. So I'm going to start substituting in the forces on the left side. The whole purpose of my picture is to start substituting in forces I'm starting to expand some of the forces. I'm going to write down all the forces. Where do I get them from? From my diagram. One thing now, the whole purpose is direction here. So plus and minus matter, like positive direction, negative direction. So I label, I'm going to say that anything pointing up is positive. Anything pointing down is negative. So now I write in the forces. I write in T plus mg, like I'm just adding up all the forces from my picture. But since mg is pointing down, I give it a minus sign, okay? I'm not saying mg, notice two things. Please notice two things. One, I'm not saying that mg is always negative. I'm just saying once you label your axes for your situation, whatever is going in the negative direction gets a negative sign. But also, please notice, and this matters for your lab, please notice that negative signs come in now. Once I label axes and start putting my arrow, plugging my arrow names into my net F, my sum of F's. But what I'm saying is G never got a negative sign. G is just G always. Like weight is M times G, not M times negative G, not M times negative 9.8. Weight is MG. Just write as MG and then make decisions about negative sign. Like don't put in two negative signs. It's not negative M, negative G or something. Anyway, you get it. But negative signs only come in now when I start transcribing my arrows into the left side of F net equals MA. So I write, and I'm summing up all the arrows. I'm adding them all up. Just some of them have negative signs. So it's T and negative MG. So it's T minus MG equals MA. But we were told that the mass was stationary. So here's another case. Because this case is fairly simple and I'm trying to show something with it, it's following all the rules, but it's fairly simple, comparatively simple. So here's another case where actually, instead of using my knowledge of F's in order to solve for A, here I actually have some knowledge of A. I'm going to plug that knowledge in order to learn something about the F's. I know that A equals 0. Like in the first example, it was G because the thing was free falling. Now I know that the fish is just sitting there. So A is 0. So I plug in 0 for A. Therefore, so T minus MG equals 0. Therefore, T equals MG. The magnitude of the tension force equals the magnitude of the weight. That's what I just learned here from this comparatively simple example. The magnitude of the tension force. So in other words, I was correct to sort of guess or surmise that my two arrows should be basically the same size. They, in fact, should be exactly the same size. The tension up equals the weight down. In this case, I'm not saying tension always equals weight at all. I'm just saying in this case. In fact, to be really specific, it's only because this fish is sitting still that I believe this. The moment I start lifting that fish, you might even want to write this down. The moment I start lifting that fish, if the fish were accelerating up, all of the facts of this procedure would be the same. The diagram would be the same. The F net equals MA statement, the substitutions would all be the same. But if the fish were accelerating up, if I were lifting the fish, then A would not be 0. It would be some positive number. So it would turn out that tension would be greater than the weight. If I'm lifting it up, the tension in the string must be greater than the weight. If I'm lowering it down, the weight must be greater than the tension. So don't think that the tension is automatically equal to the weight just because they're opposite in direction. They're equal in this case because I'm assuming in this case that the fish is stationary. In fact, and here's a lot, I know we have 15 minutes, so here's the last thing. And this is very tricky, what I'm about to say. Super important, but subtle, what I'm about to say. I'm saying the two forces in my picture are opposite in direction and they are equal in magnitude. So it raises the question. Well, so it says here. So in this, hello, oh no, there goes my board. No, no, 1 second. The question that this is going to raise, hold on, let me get the good heavens to Betsy. Who is Betsy? Okay, please excuse my dear Aunt Sally. Okay. 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 All right. So in this case, the force of tension and the force of weight, they are opposite in direction. They are, no trick. And they are equal in magnitude. They are, no trick. But so that raises the question, is this pair of forces an example of an action-reaction? Is this an example of Newton's third law? I mean, they're equal and they're opposite. Is this what Newton meant in his third law? That, oh, for every action, there's an equal and opposite reaction, or for every action, there's an equal and opposite reaction? And here's the thing. No, it's not. But here's the other thing. A lot of web pages will lead you to believe that it is. Even textbooks will lead you sometimes to believe that it is. Even teachers sometimes sound like they might be saying that it is. Not Professor Liu, I promise. But sometimes it might seem like a teacher is saying, or a web page is saying, or Chegg is saying that these two forces are an example, or that they're equal and opposite because of Newton's third law. No, totally wrong. And on all due respect, like Professor Lou would never say that, but you might sometimes think she's saying that because it could seem that way because you kind of want, but Chegg would say that because Chegg is Chegg. And I didn't say it, but I totally said it. But I need to analyze this because it's really important to Newton's third law plays a huge role in all of this, but it's a very subtle role. It's not the role that sometimes people think. Here's an example where we have two forces that are equal and they're opposite. It is not Newton's third law. Here's what I mean. What we're going to do now is what we often do. We're going to pause. We're going to look at our diagram. We've already used our diagram to solve for F net equals MA. Before we go on to any other diagrams, like on Monday, we're going to look at our diagram and list all the action-reaction pairs, all the Newton's third law action-react pairs that this diagram is capturing. Like what role is Newton's third law playing in this situation? Because it always is playing a role. It is a law. It is always true. I'm just saying it doesn't describe, and it always means that for every action, it is the case that for every action, there's an equal and opposite reaction. But I'm saying those two arrows there, one of them it's not that one of them is the action and the other is the reaction. No. What are the action and reactions? I'll show you. Because there's two arrows in our free body diagram, they don't make a pair. Each one of them is half of its own pair. If there's two arrows in a diagram, that means there's two Newton's third law pairs. Let me put it another way. Those two don't make a pair because there can't be a law that says if there's mg down, there must be tension up, because we just did an example 2 minutes ago where there was mg down and there was no t up. Like there's no law that says things are not allowed to free fall. Something can free fall. When it falls down, nothing pulls it up. If something automatically, necessarily by law had to pull it up, nothing would ever fall down. Newton's third law does not say if you are pulled one way, you must be pulled another way. That would be insane. Nothing would ever accelerate. What Newton's third law says is this, is that let's look at the mg arrow first. It says the mg arrow is an action. Yes, it's an action. And yes, there's a reaction to it. The reaction is in some other diagram that we're not seeing. The action is that the Earth, so I'm looking at the mg arrow, the Earth is pulling down on the mass. That is true. That's an action. The Earth is pulling down on the mass. According to Newton's third law, therefore, the mass is pulling up on the Earth. That's the Newton's third law pair. And by the way, that is true even in free fall, right? If there's only one thing happening, if the Earth is pulling down on a tennis ball and the tennis ball is falling toward Earth, then according to Newton's third law, the tennis ball is pulling up on Earth. And that is true. Anytime the Earth pulls me, I pull back on the Earth. The whole point of a force is that it's a symmetric interaction. It's like this whole deal of I married my wife on October 20th, 2012. Guess what? My wife married me on October 20th, 2012. It would be impossible for me to have married my wife without, at the same time, her marrying me. That's the nature of marriage, right? And I'm not even making a joke, even though that is obviously a silly example. But it's silly because you know the words so well that you know that that's just obvious. Like, duh, you can't marry someone without them marrying you. And you can say you married them, or they can say they married you. That's just a matter of how you're looking at it, right? We all understand marriage, and use whatever example you want. But marriage is a symmetric interaction. You can't go one way without, maybe one of us does it well and the other one's doing it badly. I don't know, but we're both doing it, right? We're trying to say that forces are the same way. The Earth cannot pull on something without it being a tug of war, without the other thing pulling right back on it. It's just a matter of how you look at it. It's not like one is trying and thinking about it, and the other, and that's why, by the way, the words action and reaction are a little bit bad that way. It's not really that one happened first and the other happened second, or it's not cause effect. They're just two sides of the same coin. So when the Earth pulls down on something, on a mass, the mass pulls up on the Earth. And by the way, they do it with not by the way, but very importantly, they do it with the same strength. the same number of newtons. You might say, well, wait a second. I mean, I see the object falling down really quickly, 9.8 meters per second squared. Are you telling me that the Earth is accelerating up at 9.8 meters per second squared? Because that's a hard pill to swallow. Like, I don't see that, comma, yo. But no, I'm not saying that. F equals ma. F net equals ma. I'm saying the Earth pulls me down with the same number of newtons that I pull up on the Earth. We're both pulling each other with the same force, but we're not both the same mass. I'm teeny, the Earth is ginormous. So it's like the example with me and my brother. If the same, we're each being subjected to the same force, a force called weight, a force, say I'm 1 kilogram object, then we're each being subjected to a 9.81 Newton force. But a 9.81 Newton force has a huge effect on a 1 kilogram mass, and it has a tiny negligible effect on a freaking 6 times 10 to the 24th kilogram mass like Earth. See what I'm saying? So I'm saying if the Earth pulls me down, I pull it back up with the same force, but then we don't both accelerate the same way. Force is like cause, acceleration is like effect. The effects are totally different because mass is resistance to acceleration. So back to we have 7 minutes. I'm saying the minute you have a down arrow in an FBD, that necessarily implies an up arrow in some other FBD. The reaction to mg is an up arrow that you would draw if you were drawing a picture of Earth, which we happen not to be right now. We could, but we're not caring about that right now, so we didn't. But also notice that's the other thing about the system schema. When we first drew our mass, we drew the Earth over here and we connected with the line. In the system schema, it makes it really clear. There's just these two objects that are just pulling on each other reciprocally. End of story. That's the action. So in free fall, there's one line, there's two objects connected to it. The line goes both ways. There's no arrowheads on it. The Newton's third law pair is if the Earth pulls on me, then I pull on the Earth. That is the action reaction. And it's true even in free fall. But then now in this case, we have this other arrow in the picture, the upward arrow of tension, which says that there's some fishing line pulling, some fishing rope pulling up on our mass. Okay, so rope pulls up on mass, action, therefore reaction, mass pulls down on rope. That would be in a different picture, in a picture of the rope. If the rope is pulling up on the fish, then the fish is pulling down on the rope. That's Newton's third law. That's the action-reaction pair. So every arrow in a diagram is an action to a reaction in some other diagram. As many arrows as there are in your FBD, that's how many pairs there are in the world. Put one last final way, there could be any number of forces acting on an object. There could be 0 forces on an object. There could be an odd number of forces acting on an object. There could be an even number of forces acting on an object. But there could only be an even number of forces in the universe. Forces come in pairs, but they don't act in pairs on the same object. I push you, you push me back. That's the law. There is no law that says if I am pushed one way, I must also be pushed another way. That's insane. That would mean that nothing ever accelerates. But I will tell you that if you're not careful, it's really easy to misunderstand that. A lot of web pages and a lot of books and a lot of people really, and that's why I don't say that, that's why the way I phrase the law is if A exerts a force on B, then B exerts a force on A of opposite direction and equal magnitude. What I don't just go around saying is for every action, there's an equal and opposite reaction. I'm not saying that's not true. It is true, but it's completely vague. It totally misleads us into thinking that if I right now sneezed, I would automatically have to fart. Pardon my language. But like sometimes that happens to people, but that's not a law. That doesn't have to happen. If it did, nothing would ever accelerate. Okay. Almost done. Oh, hey, I think we are done. Hang on 1 second. Weird. I think we were 1 second. Let me just see. Okay, right, okay, okay, I will say, I don't know what the resolution is. I'll just say that that Professor Lou was open to what I said. I mean, I think it depends on factors. I will say this too. If there are any guests in your room, then she might not be able to do that, and there might be guests. But apparently she had, I'll tell you this, she said that she had that on her mind as well. So it might happen. We're doing our best. Again, let it go, just let her, but message sent, message received. She was thinking that too. There's factors that might mitigate against that. Like you might have a guest, not a special guest, not like a speaking guest, but just there might be blah, blah, blah. I'm just saying, but the one thing I can say is you've been very kind. You've been very patient. You guys are awesome. I will miss you. I hope you have great turkeys. And yes, strangely, if nothing else, we can go unusually 2 minutes early. So happy Thanksgiving. But I'm here if there are any questions. Happy Thanksgiving. Yes, happy Thanksgiving. Awesome. Oh, yay, Katya. See ya. Okay, thank you. Yes, have it, all of you. Yes, thank you, Jose. I appreciate it. Thank you.
Professor, I have a quick question.
Yes, let me stop the recording.